In this video, we will talk about work. A force applied on a solid performs work when it tends to accelerate or decelerate its motion. Infinitesimal work, dW, done by a force F, is the dot product of F and the infinitesimal displacement vector dr of its point of application. Therefore, dW is equal to the magnitude of F multiplied by that of dr and multiplied by cosine alpha, which is the angle between vectors F and dr. Referring to this formula, dW equals 0 if F equals 0, which is logical since work is done by a force. So there is no work if there is no force. dW also equals 0 if dr equals 0, which means that there is no work if there is no movement. So let's not confuse the physics definition of work, which is a transfer of energy, with the everyday notion of work, which means effort. dW also equals 0 if F is perpendicular to dr. A common example of this is a satellite in a circular orbit. In this case, the gravitational force exerted by the planet on the satellite is at right angle to its infinitesimal displacement vector at any instant along its circular path, and no work is done on the satellite. Hence, the satellite orbits with no change in speed. If alpha is acute, like in figure 1, dW is greater than 0 and the force tends to accelerate the motion. In this case, the work is said to be motive. If alpha is obtuse, like in figure 2, dW is less than 0 and the force tends to decelerate the motion. In this case, the work is said to be resistive. Work done by the normal reaction N is equal to 0 since the total work W equals the sum of all the infinitesimal works equals the sum of the dot products of vector N and the infinitesimal displacement dr at any instant equals a sum of zeros since N is always perpendicular to dr. The result is 0. Work done by a friction force of constant magnitude F is equal to minus F multiplied by the total length L of the path traveled by the point of application of the force, since the total work W equals the sum of the infinitesimal works equals the sum of the dot products of vector F and dr at any instant, equals the sum of F multiplied by the magnitude of dr multiplied by cosine 180 degrees, since the direction of F is opposite to that of dr. Cosine 180 degrees is equal to -1. Minus F is a constant factor. It can be put outside the sum, and the sum of the magnitude of dr is the total length L. Work done by a constant force F is equal to the dot product of vector F and the displacement vector AB of its point of application, regardless of the path taken. Since the total work W equals the sum of the infinitesimal works equals the sum of the dot products of F and dr at any instant. Vector F is constant and can be put outside the sum, and using the head-to-tail method, the sum of the infinitesimal displacements dr is equal to vector AB regardless of the path taken. In the International System of Units, the magnitude of a force is expressed in newtons, L and AB in meters, and the work W in joules. The weight mg of an object changes with the location, but in a limited area, it can be considered as a constant force. In this case, the work done by the weight along any path from point A to point B is given by the formula W of mg equals mg dot AB equals mg multiplied by AB multiplied by cosine alpha, where alpha is the angle between vector mg and the displacement vector AB. In a Cartesian frame of reference xyz, as shown in the figure, we can write the coordinates of vector mg and those of vector AB. The dot product gives W equals minus mg multiplied by zb minus za, where b corresponds to the final position and a to the initial position. This can be written as W equals minus mg delta z if the z-axis is directed upward, as in the figure. If the z-axis is directed downward, the coordinate of vector mg of the z-axis becomes plus mg, which leads to W equals plus mg delta z. As a result, the work done by the weight is equal to plus or minus mg delta z, depending on the direction of the vertical z-axis. Now let's find a third formula to determine the work done by the weight. If the z-axis is directed downward, we can apply the formula W equals plus mg delta z. If in addition to this the body is going down, for example from A to B in the figure, delta z will be equal to zb minus za, since B and A correspond respectively to the final and initial positions. Let h be the height difference between A and B. This gives delta z equals h, since in this case zb is greater than za. The result is W equals plus mgh. If the z-axis is still directed downward, we can apply the formula W equals plus mg delta z. If in addition to this, the body is going up, for example from B to A in the figure, delta z will be equal to za minus zb, since in this case A and B correspond respectively to the final and initial positions. This gives delta z equals minus h, since, as we said, zb is greater than za. The result is W equals minus mgh. If the z-axis is directed upward, we can apply the formula W equals minus mg delta z. If in addition to this the body is going down from A to B, delta z will be equal to zb minus za. This gives delta z equals minus h, since in this case zb is less than za. The result is W equals plus mgh. If the body is going up from B to A, delta z will be equal to za minus zb. This gives delta z equals h, since as we said, zb is less than za. The result is W equals minus mgh. As a result, the work done by the weight is equal to plus or minus mgh, depending on whether the motion is downward or upward. Now let's talk about what we call conservative forces, which have these two equivalent properties. The work done by a conservative force on a particle moving between any 2 points does not depend on the path taken by the particle and is equal to 0 if the path is closed. Note that a closed path is one in which the beginning point and the end point coincide. Also note that a force is non-conservative if it does not satisfy these two properties. For example, gravitational force is a conservative force, whereas frictional force is a non-conservative force. And this is all for this video. Thank you for watching.